Hi all. Last day we have discussed how to connect the coordinates of two coordinates relative to two bases of a single vector alpha uh, using a transition matrix. Today we discuss theorem 8. We have a vector space V and a basis. We have a single basis here V consisting of vectors alpha 1, alpha 2, etc. alpha n is the basis for V. And now we are given an invertible matrix P. Okay, P is equal to Pij is the matrix which is non-singular matrix. This is determinant of P is not equal to 0. Now, using obviously this Pij comes from F, where V is the vector space over F. Now this is the hypothesis of the theorem 8. Now with these hypotheses you can construct, then there exists another basis B prime consisting of vectors alpha 1 prime, alpha 2 prime, etc. alpha n prime with the condition uh, basis this relate coordinates relative to the basis V can be connected using this P. Okay, this is the coordinate of alpha relative to the basis. This is the coordinate of alpha relative to the basis B, and this is a coordinate of alpha related to the basis B prime, and P times this P inverse times alpha relative to B is same as coordinate of alpha relative to B prime. That means if you are given a non-singular matrix and a ordered basis of V, you can construct another basis with the same condition. The last class we have discussed. Once you are given two distinct bases, you can easily find this P. Okay. Now in this theorem, using a basis and a non-singular matrix, we can construct another set of basis vectors satisfying the same relation what we have proved in the theorem 7. Okay, this is we can prove this by constructing the basis B prime first. So to construct this B prime, we choose the coefficients of the matrix P. That is, we write this alpha 1 prime, or we define this alpha 1 prime as P11 alpha 1 plus P21 alpha 2 plus etc. Pn1 alpha n. This is the first vector in this, and similarly you can define alpha n prime up to alpha n prime P 1 n alpha 1 plus P 2 n alpha 2 plus etc. P n n alpha n. So we can abbreviate this as alpha j prime is equal to P1j alpha 1 P2j alpha 2 plus etc. Pnj alpha n, and this is nothing but sigma I equal to 1 to n p I j alpha I. Okay, this is the definition of alpha j primes. So we will prove that this alpha j prime spans V, and this alpha j primes are linearly independent. And this condition is trivial once you construct this alpha j prime as in this format. We can easily get coordinate of alpha relative to beta. B is equal to p times coordinate of alpha with respect to B prime. So in order to verify this relation is verified only when this B prime is a basis. So first we will prove that this B prime spans this V. Okay, that is the first idea. So since this P is invertible, then there exists a matrix Q such that Q is equal to P inverse. So I'll write this Q as set of all Qi j. This is the matrix P inverse. Then from this you can write it as P Q is equal to identity, that is equal to Q P. So this is the relation between this Q and P. Now we construct, or if we write this j varies from 1 to n, Qjk alpha j prime. Okay, so when you expand this, you can get this q 1k alpha 1 prime plus q 2 k alpha 2 prime plus etc. Q nk alpha n prime. That is this summation. So this is equal to, this can be written as summation. The summation can be written as this alpha j prime can be replaced by this sum. So that means each alpha 1 prime can be replaced by this expression. So that is equal to sigma j equal to 1 to n q j k, and this is alpha j prime. Alpha j prime can be replaced by sigma I equal to 1 to n p I j and alpha I. Okay, this is the expression for this alpha j prime. But this is equal to sigma j equal to 1 to n and sigma I is equal to 1 to n p I j q j k p I j alpha I. Okay, now you can rewrite this summation as, or interchange this summation, sigma j equal to uh, I equal to 1 to n sigma j equal to 1 to n. This is our p I j q j k alpha I. Okay, so you can take this alpha out because this summation is, the first summation depends only on j, so you can take this I out. So now the interchanging of the summation is nothing but the order of the change of the order of the summation. So that means when you consider a11 plus a12 plus a13 uh, and a21 plus a22 plus a23, this is our 6 elements. When you add this, you can get all the sum like a11 plus a12 plus a13 plus a21 plus a22 plus a23. This sum is same as, this is equal to the sum a11 plus a21 plus a12 plus a22 plus a13 plus a23. These two sums are same. So when you write this sum as in this form, you can write it as sigma j equal to 1 to 2 sigma I equal to 1 to 3 aij. Because when you expand this sum first, I equal to 1 to 3, then you can get a for corresponding to j equal to 1, we can get a11 and this I write I is equal to 1 to 3. This is in the other way. We write that is equal to uh, write it as j, this is I, and I from write it as, we write this I is equal to, from this I write I j is equal to 1 to 3 and I is equal to 1 to 2. So when you expand this, if, first you write for corresponding to I equal to 1, we have j equal to 1 to 3. So this is a11 812 plus a13, and for corresponding to I equal to 2, you can get the other sum. But this can be written as the second sum can be written as this is same as summation j equal to 1 to 3 and summation I equal to 1 to 2 aij. Okay, when you expand this, you set j equal to 1 first, then expand this one. So j equal to 1 and I equal to 1 and 2. So you will get this one. I equal to 1 and 2 means a11 a21. So this shows that the interchange of, if the summations are finite, the interchange of these two summations it really means the order of the summations are interchanged. That's the meaning of the interchange of the summation. So that's we are using here. When you interchange these two summations, j equal to 1 to n, I equal to 1 to n to this I equal to 1 to n, then j equal to 1 to n, both will give the same thing because this contains only a finite number of terms. So the summation, yeah, the interchanging of the summation really means that the order of the summation is interchanged. So when you write this in this manner, you can say that this is actually a linear combination of alpha I. So that means sigma I equal to when you expand this, you can write something times alpha 1 or something times alpha 2, etc., something times alpha n. When you consider the summation by expanding, you can get this. This is the ikth element of the matrix PQ. The matrix PQ is nothing but the identity matrix. The identity matrix is each one on the diagonals, and first of the entries are 0. Or you can write it as delta ij. What is delta ij? Delta ij is 0 when I not equal to j, and 1 if I equal to j. This is the definition of the identity matrix. So since this is the ikth entry of PQ, you can write this element as delta ik using this. Okay? The ijth entry of PQ is delta ij. So ikth entry of this PQ is delta ik. So now you expand this sigma, or you can write it as I equal to 1 to n delta, this is ikth entry, ik and alpha I. Now you can get this is the sum as delta 1k alpha 1 plus etc. In between we have delta k alpha k plus etc. delta nk alpha n. But we know that all these quantities are 0 except for this. Okay, so that is equal to 1 times alpha k, that will give alpha k. This shows that each alpha, when you set k is equal to 1, you can get this sum as alpha 1. Similarly, when you set k is equal to 2, you can get this sum as again alpha 2, and so on. So this shows that each alpha 1 is a linear combination of alpha 1 prime, etc., alpha n prime, something into alpha n prime, and similarly alpha n can be written as something times alpha 1 prime, etc., something times alpha n prime. So this shows that each alpha 1, alpha 2, alpha n can be written as a linear combination of this vector. This shows that when we take an alpha from B using the property of the basis B consisting of alpha 1, alpha 2, alpha n, this alpha can be written as some x1 times alpha 1 plus etc., xn times alpha n. And we can replace this alpha 1 as a linear combination of alpha 1 prime, etc. So similarly, each element is a linear combination of again alpha 1 prime plus etc. alpha something into alpha n prime. That is the span of alpha 1, alpha 2, etc. alpha n is same as span of alpha 1 prime, etc. alpha n prime. So that the span of alpha 1, alpha 2, etc. alpha n is nothing but V. Therefore, this V prime consisting of alpha 1 prime, etc. alpha n prime spans V, and hence a basis. And hence a basis, because if this is not linearly independent, then there exists a subset, proper subset of this which is linearly independent and spans the same span of B prime, that is equal to V. So which is a contradiction for the dimension of V, then dimension of V would be less than n, so there is a contradiction. So we can say that B prime is always a basis. So now we have B and B prime are bases, okay, are bases of V, and hence the previous work shows that from these we can say that these relations holds. The basis, the coordinates relative to V is same as P times the coordinate relative to B prime. Okay. Now the idea is, first we take this B and the entries of P, construct this B prime, and we have shown that this B prime is a basis again by showing that this spans V. Okay, the ones we have proved that B and B prime are bases, by the construction of these alpha j primes, we can say that this trivially hold. This we have discussed in theorem 7 as well. So this proves theorem 8. And now we can, and the next class we will see some examples of examples explaining or illustrative examples of these two theorems.